Hi everybody. In this video, we are going to see how we can use our dataset and train several machine learning algorithms in order to get some forecasting model. We are going to see how we treat our data, how we use different algorithms, what type of results we get, and of course, how we can select the best model among all the models that we train. And of course, we're going to do all this using this software called Orange. Orange is very interesting. It's very nice for several reasons. First of all, we can use, we can train machine learning algorithms with Orange very easily. Second, Orange is free, so this is very important. Third, it has a very nice GUI, graphical user interface, so it is easy for the newcomers in machine learning to use it and get an idea how machine learning works. And finally, it is powerful enough for most analysis, from rough analysis to precise analysis that we can perform with Orange, because again, under the hood there is Python. Now, let's get started. As you can see here, we start from the left and we end up on the right. Here we have the file that we are going to use, our data. In order to import our data, we click here. Of course, now my file is already imported here in Orange, but when you try for the first time to import your file, you go, you press that button, you go here, importing this dataset, credit card forecasting 400. Now I have data from credit card customers from a bank with the information, the customer number, whether they are employed or not. As you can see here, already Orange recognized this variable as categorical. But then it also recognizes the customer number as a numerical variable, where we are not going to use this because it is not an actual variable. This is just a code number for each one to differentiate between the customers. This is a meta variable, and we can change it. Here. As you can see, I'm going to put this as a meta variable. All these are features. Okay, these are the variables that we're going to use. Whether the customer is employed or unemployed, we have 0 and 1, 0 for unemployed, 1 for employed. Whether he or she owns a house, again 0, she does not own a house, 1 owns a house. In this variable balance, we have the actual balance on their credit card. Income is their annual income, and this variable no pay, this is again a categorical variable with values 0 and 1, and we have a 0 here whenever a customer pays, and 1 whenever a customer does not pay. So whenever we see 1, it means that we have a no pay condition, some bad customer, and when we see 0, it is a good customer for the bank. Now, just as we did with the customer, that we marked this as meta and not an actual feature, now we're going to mark this, the no pay, as our target variable, because this is the variable that we want to forecast. Okay, we can press apply here, so we can get the data. Okay, now the data are imported in Orange. And this thing here, this is my pipeline. This is the workflow that we're doing. Automatically, Orange has performed all the analysis now behind the scenes, but we're going to see each individual node here. We started with the file where we imported our data. Now we have this branch here where we have some both visual inspection of the data. We always have to visually inspect our data to see whether there are some outliers or there are some other missing values, some problems with our data, and so on. So we always start with that. As you can see here, we can create many different graphs. We can color them, change everything. It is very nice. We can produce any type of graph. Also here we have the feature statistics. So we have the descriptive statistics of our variables, our features. This is, for example, here for the balance, we have the mean value, the mode, the median, the dispersion, minimum values, max values, and whether we have any missing values. As you can see here, we have no missing values, so we can proceed. And the other descriptive statistics are very simple because all of these variables are categorical variables. They are binary variables. And also here we can create some calculate some correlations between the variables. I just put it here. Of course, we can put several different things when we select them from this area here, from orange, but just for an illustration, I put these three things that are still important. So after this visual inspection of the data, now we can start the analysis. I have inserted here this node, the color node. We can create different colors for different values of our variables. So this is nice for the graphs. It does nothing in the actual analysis. And next we have the data table. So these are all our data colored. As you can see, we have now this is customer 1, 2, 3 up to 400. Here, as you can see, we have 400 customers. The no pay data, this is our target variable. Again, whether he or she is employed or owns a house, the balance on the credit card, the income. Also, we have some small graphs here. We can change all these. As you can see here, visualize numeric values. Of course, this is all of this is very interesting to put it on a report, on a paper, on a dissertation or a thesis, and very easy to produce. So this is the node data table. Next, we have this node select columns. What we do here is we actually assign different roles to the different variables. Even if we didn't do it at first here in this area file, now we can do it here. What we do here, let's say we didn't do it before, so we have something like this. All variables would have been there. So we have these variables. This is my target variable. I can drag it here as a target to designate it as a target variable. All these variables that are left here in this window are the features that we are going to use. In other words, these are our independent variables. And in this area here, I have the variables, the columns from Excel that are going to be ignored, as you can see here. And we are going to ignore this because this is just text. And it is the customer number that plays no role in forecasting whether the customer is going to pay or not their credit card. Next, I have here this node pre-process. If we want, if there is a need for several reasons, we can pre-process our data. I didn't do it here, and you can see that because this node is not connected to any other node here. As you can see, we can do several different things with Orange to pre-process, and we can actually include more than one pre-processing algorithms before going to the actual models. But we do not have to do it here, so I leave it outside. Now we go to the data sampler. This is an important node. Parenthesis here. You can see that we can move everything wherever we want. Take a look. We can move everything. It is very adaptable, so it is very nice to have this visual interpretation of the pipeline of the models. Now, let's go back to the data sampler. The data sampler now, double click, is important because we select this one. Of course, again, another parenthesis, there are a lot of selections, a lot of very different things we can do with Orange. Here, I'm only using the basic ones, the easiest ones, and the most efficient ones, I can say, to produce nicely trained machine learning models. So here what we do, we select this fixed proportionality of data. Basically what we do in this node, the data sampler, is now that we define which part of the data is going to be used as the training data and what part of the data is going to be used as the test data. Here I keep the default value at 80%, so 80% of the data are going to be used to train the models, the different machine learning algorithms, and 20% of the data are going to be left outside. They are not going to be used, seen, or by any means have anything to do with the algorithms. They are left aside, and these are kept as the validation subset, so we can see how well our best model performs to new and unknown data. A note here for those of you who wonder, here the cross-validation is not selected. This doesn't mean that we're not going to perform cross-validation, because otherwise we're going to get an overfitted model. But we can do this in the next step, and it is better to do it in the next steps, the cross-validation. Here we only separate the data between the training data and the validation set, the out of sample data. Of course, we can do bootstrapping here. We can we can check this to have replicable sampling. So Orange always selects the same every time we run this. Orange always selects the same 80% of the data. So we have consistent and comparable results, or we can stratify the sample whenever there is a need to have a stratified sample. I leave it like this. So we just separated the data into the 80% of the 400 parameters. Our initial data set included 400 observations. So 80% of that, 320 observations, are now subsequently going to be used to train the machine learning algorithms, and 20%, 8 observations, are going to be used for to test our best trained models as a validation set. And finally, after all this pre-processing, visual inspection, determining the in-sample and out-of-sample data and all that, we are going to the actual training of the models, the actual machine learning models. As you can see here, I have included, of course, you can include only one. You can select and delete all of this and keep only one, or you can include different instances of the same algorithm, but with different specifications. For example, as you can see here, I have the SVM node algorithm, but here, as you can see, with a linear kernel. Now here I have the SVM with a polynomial kernel, the SVM with the RBF, and the sigmoid kernel. So we have a total here of 1, 2, 3, 4 support vector machines algorithms. I have the k-nearest neighbors algorithm. I have the gradient boosting algorithm, the random forest, random forest, a decision tree, the logistic regression, and a neural network. So I have a lot of alternative machine learning algorithms included in this. They're connected like this. Don't ask me why. This is how we have to connect it to get the results from Orange. And now we move on to this very important node here, the test and score. That now actually our models are already trained. Okay, because we have a few observations, only 320 observations, and like 3 or 4 independent variables. So it is fast. It doesn't take a lot of time to train the models. And Orange performs the training implicitly from the start when we selected the data set. Now, let's go back to this, test and score. Test and score is probably the most important node here, because if you double click, you are going to see here, we have all the information from, let me arrange this better. We have all the information from the training. What we need to see here, we go here, we press on this, test on trained data. This is going to provide the actual results on the training data. Again, let me arrange this. This is annoying, but anyways. Okay, these are the actual results on the training data. As you can see, we have extremely good results. Probably here we either have overfitting or the data set is very easy to forecast. But nonetheless, these are our training data results. You can click here to sort the different machine learning algorithms here, the different models, according to each individual performance forecasting evaluation criteria, the area under the curve, the F1 score, precision, recall, and so on. Now, depending on the type of problem we have at hand, one or two of those forecast criteria may be more relevant. But in general, here you can see, you can select which model is the best, is the most efficient one in forecasting whether a customer is going to pay or not his or her credit card. So these are the results on the training data. And now if I press here, as you can see here, also Orange mentions this, that we have 320 observations, okay, and 320 observations. This is our training set. And if I press here, now Orange is going to use the trained models on the 20% of the data that we left aside as test data, or the validation data, depends on the terminology that we use, and it is a bit confusing. But these are the out of sample data, the test data. Now, as you can see, we can now we get the results. I like to see it like this. I think it looks better. Okay. Now, let's say we select the model according to the AUC. So we press here, the worst model is the decision tree model, then with the logistic regression and so on. If I press again, now the best model out of all the 10, 12 models that are trained is the support vector machines with the support vector machines model with the linear kernel. Okay, according to these results. If we select the best model according to the precision, then the gradient boosting is the best model. According to recall, again, the gradient boosting. But I told you this depends on the type of problem we have at hand. So let's go back to the training data. It trains again. Okay, let me arrange this. Okay. As I said before, we have the best model here because we have an area under the curve equal to 1, so probably we have overfitting, and of course we have overfitting here because we did not use cross-validation yet. To perform cross-validation, we check this, we select the number of faults that we want to use. We can leave it for now at 5. We check this, and now you can see that the model is, all the models are trained again in 5 faults. Of course, it takes a bit more time because we do the same thing in 5 different faults, so it takes 5 times the time that it took before. And now these are efficient results, and by efficient I mean we do not have overfitting. Okay, now let's sort again with the area under the curve. The worst model is the support vector machines with the sigmoid kernel with the 0.764 area under the curve. The best model is the support vector machine linear. Next, if we want, we can use some other cross-validation methods here. We can use a stratified or not, but this is the simplest thing that we can do, and we're going to use only this for this video. Again, if we press on test on the test data, then this model that we train with cross-validation is going now to be used on the test data, the 80 observations, 20% of the initial 400 observations that we left aside. If we press here, now we can get the actual forecast from each one of the models. Oops. Okay, as you can see, where is it? Here. Now we can, for example, this is the first observation. This is the actual value, and this is what the random forest model predicted. The actual value is 1, the random forest predicted 1, the KNN predicted 1, and so on, but the logistic regression predicted 0. So we have all these values here, all the analysis, and the independent variables here for reference. So we have every detail that we may need in our analysis. But also in Orange, as I told you before, you can get the same information from different sources. This can be either a good or a bad thing. I don't know. Sometimes it's good because you can find the same thing you need in different options, but it may be a bad thing because it is a bit confusing sometimes. Okay. Just as we saw the results, the predictions, the actual predictions per model before here by pressing this, we can also get the same information if we insert this predictions node. If we double click this, again, as you can see, we have the actual values here, the values predicted by each individual algorithm. This is the actual value that we get from the algorithm, and this is translated in either 0 and 1 if you wonder what these numbers are. And finally, we have the independent variables at the end. Next, let's go to the ROC analysis. Now, double click here, and we get the ROC curves for each one of the models. As you can see here, now all models are selected, so we have a lot of ROC curves. You can unselect the models that you want. Let's say we keep only the SVM linear. that was the best. We selected it as the best model. Where is it? SVM linear. This is the actual ROC curve for the SVM linear model. And of course, we can compare it with something else. Let's say the gradient boosting model. Okay, we get the actual values here of the. One second. The numbers, the numbers that you see here are the actual thresholds used for classification between the two classes. So here for the, let me erase this for a moment. So for the support vector machines linear model, the threshold is 0.483. So whenever we get a value above that, this is classified as 1. Whenever we get a value below that, the model classifies this as a 0. If I keep the gradient boosting model here, now the threshold for the gradient boosting model is 0.606. If you're not familiar with what an ROC curve is, please read about it. See watch some videos from YouTube. Basically, the threshold. See here, we start with a threshold of 0, and as we trace the ROC curve, okay. The threshold goes from 0 to 1. Now, for example, here in the support vector machine polynomial kernel, when we start here, you get that the threshold, as you can see, the threshold is 0.059, then it gets up to 0.08, 0.152, 0.295. The one selected here, this is why you have this line here, the one selected by automatically by the algorithm is the 0.510. Why select this? Because it is the best in terms of forecasting both classes. And here the threshold goes up to 0.787, 0.886, and this is 0.9, close to 1 in that area. So basically, when we are somewhere here, and something has a predicted probability of greater than 0.9, then it is classified into the one class, and with a value less than 0.9, it is classified to the other side. Of course, it all depends on what target, what is our target variable. It can either be 0 or 1. All these analysis here, all these, let me select them again. All these ROC curves are relevant for when we talk about class 0, so the customers that actually pay. So the no pay target variable is 0, which means that the customer actually pays. So the sensitivity we see here is how well we predict a customer that pays. We can change this and focus on how well a customer to predict, and focus on the customers that do not pay. So if I put here 1, as you can see, all ROC curves now changed. Now we measure here the sensitivity for class 1, how well we forecast the customers that are not going to pay their credit cards. And of course, similarly, on the horizontal axis now, we have the 1 minus specificity, or the false alarms that someone will not pay. For example, let me again keep only some of these ROC curves so it's not confusing. So I kept only the gradient boosting here. So the best model is here, which means that in this here the model, okay, it predicts class 1, the customers that are not going to pay, with a probability of more than 80%. Actually, it is close to 85%. But also, we have a false positive rate, FP rate. The false positive rate is equal to 1 minus specificity, or in other words, we call that as false alarm because it is a false positive. We identify someone as a customer that is not going to pay, but he pays. So this is a false positive. Since our positive is this variable here, is the target is 1. So in this case, this model identifies 85% of all customers that are not going to pay, but also it produces, you see it's close to this line here, also it produces 10% of false alarms. Or in other words, from the people that identify as non-payers, 10% are false positive. So this means that these people are going to actually pay. Of course, the more we move to this area here, the more we increase our accuracy on predicting the customers that are not going to pay, because as you can see, for example, somewhere here, the sensitivity of predicting the customers that do not pay is close to, 98%, but this comes to a cost. There is a trade-off there. This comes to a cost of a lot of false alarms. The false alarms for this point here is, 42, 45%. So it's a lot. Okay. Again, each point we select on the actual ROC curve depends on the actual problem that we forecast. If the problem, the significance of being wrong, not being able to forecast class 1 and 0 is almost the same. Let's say we try to forecast whether a stock is going to go up or down. So basically it is the same. The cost of a false forecasting, a bad forecasting, is almost the same. But let's say in cases where it is very important to forecast this specific class, in this case class 1, is very important. For example, this is a fire alarm. Whenever we have a fire in our house, then we may allow a model being somewhere here. So we have a 98% chance of detecting a fire. So 98 of 100 fires are going to be detected, and the alarm is going to sound. But we're going to have 40% false alarms. So sometimes at night we are going to hear the alarm and there is no fire. But as you can see, this trade-off between, let's say, this point when the significance of false prediction is the same, like in the stock that I told you earlier. In this case, it is maybe preferable to move to somewhere here because it is more important, or the cost to the cost to misclassify an actual fire is much higher than the cost of misclassifying a no fire situation, because in the first case, my house, even worse, the people that I love may have a problem with the fire, but in the second case, so the cost in the first case is very high, but in the second case, the cost is relatively low. I'm going to wake up at night and see that there is no fire. I'm going to be upset, and I'm going to lose, 10, 15 minutes of sleep. What is also very useful here I'm not going to explain it in detail here, we have to play with it to see. What is very interesting with, very helpful with Orange here is that it lets us quantify and put values to the cost between the two classes. As you can see here, we have false positive cost 100 and false negative cost 100. So basically, we say here that the cost of the two misclassifications is exactly the same. Okay. Now, if we, for example, let's say the cost of a false positive, a false negative, let's say, is not 100, but let's say is 5 times more important, more costly than the false positive, and I put here 500, then, as you can see, now the best model moved from this area here to that area here. Now we have more, we're more accurate in forecasting class 1, and this comes to a cost of more false alarms. So from this point, we move to this point. Now, if it is extremely important to forecast the fire, I'm going to put 1,000 here, so 10 times more costly to misclassify a fire than misclassify a no fire. As you can see, the model moves to this area. We are close to 98% of accuracy in forecasting class 1, the possibility of a fire, or in our model, someone that is not going to pay their credit card balance. But this comes to with the cost of more false alarms. So you can play with this depending on the problem. It's very interesting, and if you have an actual cost function that connects the two classes, class 1 and class 0, it is perfect to use it here. Now let's move. Next, I'm going to show you the confusion matrix. Now we have the confusion matrix here. Let's say for the SVM linear, we have again all the models here. So I'm selecting, highlighting the SVM linear, and now we have the results for the SVM model with the linear kernel. So how we interpret this? So for the SVM linear model, you see we have 320 observations in total. This is our training sample here. And the actual cases are, we have 0 cases, so people that actually paid 220, and actual people that did not pay that are 100, so a total of 320 customers. From the 220 actually good customers, we forecasted correctly 89, our model, the SVM linear, forecast correctly in the training set 89.5% of all cases, of all observations, and misclassifies 17.4%. Everything you see in blue are the successes, the correct classifications, and everything you see with red are the misclassifications. So on the other hand, for the classes of 100, we had in the sample 100 customers that did not pay. We forecasted correctly that they are not going to pay 82.6%, and we misclassified 10.5%. So basically, 10.5% out of 100 customers, we misclassified 10 customers. We predict with our model that they are going to pay, and actually they do not pay. This is how, in Orange, the confusion matrix works. If we go, as you can see here, it says show proportion of predicted. If you go here to number of instances, you get the actual numbers now, not percentages. So out of the 220 people, 204 were predicted out of the 220 that actually are good customers, they pay. 204 were predicted as good customers, but 16 were predicted as bad customers. And out of the 100 people but did not pay. We identified correctly 76 out of the 100 non-payers, and we misclassified 24 of them. We identified them as good customers. And also, you can play here with this. Now, these are, as I said before, these are the actual instances of people. If we go to proportion of predicted, so these are the probabilities, the percentage according to what we predicted. Okay, according to predicted. If we go here, it is according to the actual values. And some probabilities you don't have to use it is confusing. So these are the actual numbers of people. It is clear, and depending on what we divide it with, we get the different proportions here. Okay, let's explain this. It's interesting because otherwise it is confusing. So these are the actual instances. Okay, now if we go to proportion of predicted, this means that predicted is here. So we predicted all these people as good customers. So we predicted 228 people as good customers. From those, 89.5 were correctly predicted as good customers, but 10.5% were actually bad customers. Okay, and from the people that we predicted, 92 people that we predicted as bad customers, this prediction was correct for 82.6% of those customers, but we misclassified. We predicted as ones 17.4%, while they were actually good customers. And if we go to proportion of actual, now we do the same for the rows. Okay, from the actuals, which means that the actual number of zeros of good customers is 220. We predicted correctly 92.7%. We misclassified as ones 7.3%. Of course, for the people that were actually bad customers, they did not pay the credit cards once. There were a total of 100 people. We predicted as ones bad customers 76% of them, and we misclassified 24% of those people. Finally, here, what some other things that we can do. For example, as you can see here, these have a data table here and a scatter plot here, but they're not actually, they're connected, but they do not get data from the confusion matrix. This is why we have the dashed lines and not the continuous line, like all the other connections. This is because it doesn't get any data yet. Now, as you can see, when I press select correct or select misclassified, then these lines are going to get data and they're going to be continuous lines. Why would I want to do that? Let's say we have these misclassifications here, and we want to see which exactly observations are the ones that we misclassified. Okay, so we press here, I'm going to click here on select misclassified, and Orange is going to send from the confusion matrix the results, only the misclassified observations to the data table and the scatter plot. I click, and as you can see, now I have a data table, and here I have only 40 observations that were misclassified, and also I can get a graph of the misclassified observations for my use and see why exactly, or find patterns, or find something, I don't know, some mistakes in the data, some errors, why these were actually misclassified. Again, I can press clear the selection, and now again the lines become dashed lines again. As you can see here, the total misclassifications that we have according to this model out of the 320 observations are 24, this diagonal here, 24 actual actual ones that 24 actual ones that we predicted as zeros, and 16 actual zeros that we predicted as ones. So in total, there are 24 plus 16. We have 40, exactly 40 misclassifications. So if I press select misclassified, this is why I have exactly 40 observations here. These are all the misclassified observations. And now, if I know my data, and if I'm curious to see why I misclassified these exact observations, I may be able to find important information only from this misclassified observation. As you can see, or misclassified. This is the no pay, the actual target, the true value, and this is the value according to the SVM linear. Again, these are the results only from the support vector machines with the linear kernel, because here in the confusion matrix I selected this. If I select, let's say, the tree, okay, I have different numbers here, and now I can select and send to the table in the graph the misclassified from this one. Now I have 42 misclassified observations. Okay. What else is left here? I have this stacking algorithm. Here you can read about stacking algorithms. Basically, what they do, the stacking algorithms, they take the decisions, the forecasts from. I connected the stacking algorithm to these 1, 2, 3, 4 machine learning algorithms. So basically, each one of these algorithms votes, and the final vote is according to the majority of these 4 models. And this is how here stacking selects the target, forecast the target variable. Of course, I can connect it with all the forecasting algorithms here. What else is okay? We can also use a feature importance, the feature importance measure according to all of these parameters here, to select which variables are the most important. In this case, I have a few, and they are almost all important. But also in this model, you can see that the most important variable is the balance. Whether a customer owns a house or is employed, it doesn't play a very big role in forecasting whether he or she is going to pay the credit card or not. At least according to the AUC criterion. If we go to the precision, it's a slightly different picture, but you see, it's the bottom line, the qualitative results, the qualitative interpretation is exactly the same. Here I connected the feature importance. These feature importance results are from the SVM linear model. There is no particular reason why I used this. I only wanted to illustrate this feature here, the feature importance measure, and I put it here. This is how you connect it. It's a bit tricky here. You get the data sample data connection from the data sampler, and you get the here, as you can see, from the model connector for feature importance. So if I want to create the feature importance from my best model, that, if I remember correctly, was yes, it was actually this way I connected there. Yes, now I remember. It was the SVM linear. If I want to do the same thing for a random forest or for the gradient boosting model, then I will have to connect it like this. Make a connection here, data sample data, but in this case to the gradient boosting algorithm, and also connect the model to the model of the feature importance node. Also, I can have multiple feature important nodes. Right, I can right click here and have feature importance, have another node and put it here and connect it to a different algorithm. I can have as many feature important nodes as I want. And the last thing I want to note here is this ICE node comes from the explaining part of machine learning. As you can see here, it's included here in the explain menu. What we do here in the ICE, what we do is that produce the partial dependence plots, PDPs. PDPs are a way, provide us with a way to open the black box of these machine learning algorithms. In my example here, you can see that, for example, this is the PDP for the balance variable. That was the most important variable. What we see here is that the more we increase the balance, the probability, let's put here 1, the class that we care about, the people that are not going to pay their credit cards. As we can see here, we see that there is a monotonous relationship between the balance, monotonous positive relationship here between the balance and the probability that someone is not going to pay. So if we increase the balance from this to that of the credit card, we can see that the probability of not paying the credit card goes from 20%, if we go here, to 75%. This is the interpretation of these PDPs. Usually in the PDPs, the balance should be measured by the actual absolute values of the data set. But I think, I'm not sure, I have to check, but I think Orange here uses standard deviations. So these are +1 standard deviation from the mean balance, +2 standard deviations, -1 standard deviation, -2 standard deviations. So people that have a balance -1 standard deviation from the mean compared to the people that have 1 standard deviation from the mean balance in their credit card, have a huge difference in their probability of not paying the card. For the first ones, it is close to 0. For the second ones, it is close to 80%, 75 to 80%. This is how we interpret this. And of course, if we put here 0, then we do the same for class 0, people that are going to pay. And in that case, we have again a monotonous relationship that is a negative one. Okay. The income in this case, as you can see, let me put it again, 0. As the income increases, we have a lower probability that someone is going to pay now, because we have a 0 target class here, their credit card. So that's it. These are the most important things, I think, in training models with Orange. Remember, let me close this. Remember that once you create the workflow, this pipeline, then it is easy to train new models, because you just have to input a new data set. Of course, I explained everything here. We're using a data set where the dependent variable is a categorical variable, is a binary variable. So we have a classification problem, but very few things change when when your target variable is a continuous variable and you have a regression problem. Of course, some metrics and stuff like that change, but the basic idea is 95% the same. So you input your data, and you must be able, once you have set up your workflow, your pipeline, you must be able then to explain what you get, because you have all the results here. Again, you can add a lot of other things, as I explained before, with Orange. You can actually add Python code. Okay, we have this node here where you can add actual Python scripts. You can find a script that does a nice visualization, that performs some pre-processing or some, I don't know, whatever, a new algorithm that you want to use, and you insert it here with using that node of Python script. So basically, you can do everything. Final note, these are the default algorithms, but if you want, you can, of course, fine-tune these algorithms. For example, I double click here in the KNN. The KNN now it's a 3 nearest neighbors according to this default setting. You can change it to 2. As you can see, it's just recalculated, retrained the algorithm to 3, 4, 5, whatever you want. So this is how we may be able to optimize even further our trained models in more detail. Anything you do not understand, just search on the internet. There is a excellent documentation by Orange. Let me show you. So, for example, we are here in the confusion matrix. You don't know what the confusion matrix is, so you want some details. If you press the question mark here, you get the documentation. Your browser opens and you get all the information. You have examples, you have the definitions, you have everything that you need to know, and it is very easy to understand. Let's say test and score. Again, press the question mark, test and score. What are the inputs? What are the outputs? Explains the widget, what you see in every portion of this table, and everything is here with examples, and it is easy to understand. And also, of course, you can search a lot of videos. There are a lot of videos on YouTube that explain all these things, and of course, in general, in machine learning, exceptionally well. So that's it. Thank you very much.